All right, so this is going to be our fourth week for the engineering economics course, and in this week we are going to study the problems related to unknown investment years and unknown interest rates. Now, the outline is as follows. First, we are going to cover the linear interpolation concept because when we are going to use the compound interest tables to determine the unknown number of years or unknown interest rate in any problem, linear interpolation is just going to be a useful tool. So first we are going to learn how to use linear interpolation to determine the interest factors, compound factors for unavailable number of years and unavailable interest rates. And then we are going to first focus on the unknown number of years problem. So we are going to study over different types of cash flows, for example, where we only have a principal and a future value, or where we have a uniform series and a future value, or where we have a uniform series and principal value. And we are going to determine the necessary number of years that creates the equivalence between these cash flows. And then we are going to focus on the second type of problem, which is the unknown interest rate problem. The unknown interest rate problem is very easy for cash flow structures where we only have principal values and future values, which means a single cash flow structure. However, for general problems, it is just going to be a little hard, and we are going to study the cases where we have uniform series and other types of series to determine the unknown interest rate to create an equivalence. So first focus on the linear interpolation. Okay. Now, if you have realized the values in the compound interest tables in any column are usually increasing or decreasing. Okay. So basically, compound factors are monotone and nonlinear functions of the number of interest periods and the interest rate I%. Now, let me show you that by sharing the compound interest table. And I'm just going to explain this to you. Now, suppose that you have fixed the interest rate to a certain one, just like 0.25%. Now, if you increase the value of n, if you increase the number of investment years, you will realize that the values in the first column, which is single payment compound amount factor, will always be increasing. The values in the second column will always be increasing. The values in the third column, the capital recovery factor, will always be decreasing, and the gradient series factor will always be increasing. Therefore, when the interest rate is fixed, the compound amount factors and the capital recovery factor and the gradient series factor are just monotone functions of the number of investment years. As the number of years increase, these values monotonely increase or decrease. So they are just monotone functions. Similarly, if you fix the number of years, so let's just stick to the number of years of 10 as it is shown here. Now, please focus on the first column. So we have the single payment compound amount factor as 1.0253 for 0.25% interest rate. As I change the pages, you will realize that for fixed number of years, this value is just going to increase. So you see, the values are always increasing. Similarly, the other values are also, so starting from the smallest of the percentage values, the other values are also changing monotonely. So uniform series compound amount factor is always increasing, and capital recovery factor is always increasing, and the gradient series factor is always decreasing. So for fixed interest rate, the compound amount factors will be monotone functions of the number of investment years, as well as for a fixed number of years, they are going to be monotone functions of the interest rates. Okay, so practically we have seen these results. So what is it going to help us actually? So what we are going to use these monotone the nonlinear, what we are going to use these monotone nonlinear functions for. Now let's just say we are interested in a compound amount factor for which there is not a row that corresponds to the number of investment years or an interest rate that as a page. Okay? So you are just looking for a compound amount factor which do not exist in that table. Now you can use linear interpolation between available values and linearly approximate that intermediate compound amount factor from the table. So this is just a way to determine the compound amount factors which are not available in the table. However, it is just an approximate way. It is approximation. Remember now, it is always best to use the formulas for compound amount factors. However, it is also possible that, I mean, if you do not have a computer, you can use your tables, and if the values that you are looking for, a compound interest rate that you are looking for is not available in these tables, you can apply linear interpolation between the available values and approximate that value of interest. Now, how does it work? How does the linear interpolation work? Now, we have shown that all these compound amount factors are monotone functions. Okay, monotone nonlinear functions. So we are just going to explain the linear interpolation for a general monotone nonlinear function. So monotone means what? A monotone function is either always increasing or always decreasing. So monotone, actually, we should not say that it is always increasing, but it is not decreasing or it is not increasing, we should say. So, but I mean, in our cases, we, in the compound amount factors, we either see an always increasing or an always decreasing compound amount factor values, right? So suppose that you have a monotone nonlinear function that is f here. So this black thick line is your nonlinear function, monotone nonlinear function. And you know that this monotone nonlinear function shows y1 value for the input x1 and shows y2 value for the input x2. Okay, so let me zoom in a little so you can see better in the video. So this monotone nonlinear function shows y1 at x1 and y2 at x2. And what we know about this function is only these two values. The other intermediate values for this function are not available, and they are unknown. And we are interested in the function response at an intermediate value of x. And that function response is actually y, but we do not know it yet, and we are interested in finding that one. Suppose now there is not a formula for this function. So what we know is we only know the responses at x1 and x2 as y1 and y2. And what we know also is that this function is a monotone function, which means from that point to that point, it is increasing, or maybe we may have decreasing type of functions as well. All right, so we are going to apply a linear interpolation between these two values. And we are going to assume that between x1 and x2, this function is not nonlinear, but it is assumed as linear. So this dotted line, this dashed line, shows a linear approximation between x1 and x2 values. And instead of finding the actual response at x, which is y here, we are going to determine the approximate response, which is obtained by this linear interpolation. And we will be finding y prime value here. And actually, it is very easy to find because of the linear function that we are developing. Okay, so we know how to formulate the linear function, which goes through 2 points over a two-dimensional domain. However, I'm just going to show you another trick to determine that. Now, you see this in this picture, the y prime value here will just be an average of y1 and y2, but it's not going to be an ordinary average. It is just going to be a weighted average. So we are going to multiply y1 with a value between 0 and 1, and y2 is just going to be multiplied with 1 minus that value. Okay, so not an ordinary average, are multiplying y1 and y2 with weights defined between 0 and 1, so such that their summation is equal to 1. And obviously, we need to determine these weights. Now, you see in this example, y prime, actually not y prime, but x here, x is much more closer to x2 than x1. Therefore, the y prime value that we are going to calculate is just going to be much more closer to y2 than y1. Okay. Therefore, this means the weight of y2 should be larger than the weight of y1. So how do we determine the weight of y2? The weight of y2 should be proportional with the distance of x between x1, and the weight of y1 should be proportional to the distance between x2 and x. So what we are going to do is this. In order to determine y prime, we are going to multiply y2 with the distance between x1 and x, and y1 will be multiplied with the distance between x2 and x. And then we are going to calculate the summation, and the summation will be divided by the total distance between x2 and x1, which is exactly that formulation. So if it is impossible for us to determine the actual response for the function, we are going to approximate it with a linear interpolation. And for the linear interpolation part, the y1 prime response will be calculated as a weighted average of y1 and y2, where the weight of y1 will be equal to the distance between x2 and x, proportional to the total distance between x2 and x1, and the weight of y2 will be the distance between x and x1, proportional to the total distance between x2 and x1. So when you divide these distances, x2 minus x and x minus x1, to the total distance between x2 and x1, these values are just going to be two values between 0 and 1, and they will sum up to 1. Therefore, they will be considered as the weights of y1 and y2. What you need to be careful here, y1 is going to be multiplied with the opposite distance between x2 and x, and y2 will be multiplied with the opposite distance between x1 and x. Now, why we are doing this? Because of the similarity of the triangles. As you know that the proportion of the distance between y prime and y1 and y2 and y prime will exactly be equal to the proportion between x and x1 and x2 and x. Okay, so we know this by the similarities of the triangles from our earlier education in high school or mid school, and we can use that fact to linearly interpolate a function between 2 points, and we can find the approximate value by this linear interpolation. All right, so this is how it works. Now we are going to explain the inverse linear interpolation, which means you can also do the opposite of linear interpolation. Now again, we consider there is a monotone function between x1 and x2 values. We know the response at x1 is equal to y1, and the response at x2 is equal to y2, just like in the previous example. This time, we are not interested in finding the response for an intermediate x value, but we are going to do the opposite of it. We will be interested in the inverse of f. So we are going to ask this question. For which value of x the response would be equal to y? So we are looking for the input value for which the response would be equal to y. And actually, if we just draw a horizontal line from this response value, the actual input value is supposed to be x. However, since we do not have any formulation for the inverse function, and for most of the compound factors, you will realize that there is not an inverse function. Okay, you are going to learn about it in the following videos of today's chapter. So when the inverse function is not available, the only thing that you are going to be able to do is you will be linearly interpolating that function between x1 and x2, and you are going to look at the projection over the horizontal axis which goes through the linear line instead of the actual nonlinear line. So we are going to be interested in the x prime value as an approximation for the x value, and that is going to be our result. And how do we determine that x prime value? So here you can see it. We are looking for the input x value for which the inverse of f function at y is equal to that value. However, that is just going to be approximated linearly by this function. And this time, you see, we know that this x prime value is just going to be somewhere between x1 and x2 due to the monotonicity of the function. And we can calculate that x prime value as a weighted average of x1 and x2. And how do we determine the weights? The weight of x2 will be proportional to the distance between y and y1. And the weight of x1 will be proportional to the distance between y2 and y. This time we are going to multiply x1 with y2 minus y, the opposite distance, and x2 will be multiplied with y minus y1, and the summation of these values will be divided to the distance, total distance between y2 and y1. So basically, the weighted average is taken by weighting x1 with a weight that is proportional to the distance between y2 and y, and the weight of x2 is going to be proportional to the distance between y and y1. Okay. So basically, we are doing the opposite of the linear interpolation that we have done, and that is called the inverse linear interpolation. But the logic and the story is actually the same. The only thing that is changing is you are swapping the axis. So you are looking for the x value instead of a y value. And in this course, we are going to use both of these linear interpolations in different questions. Now, here in this first question, we are going to practice our first linear interpolation, and it says approximate the f over p value under 8% interest rate for 37 years. Now, actually, you know that you can calculate that value using a simple formula, right? The value will be simply 1.08 to the power 37. Okay. Now, you can also determine this value by applying a multiplicative relationship over the f over p values, for example, at 35 years and 2 more years. Okay. But today, we are going to find this value with a linear interpolation technique. Actually, the other two methods are much better to use, and the values will be almost exact values in the other methods. So interpolation, applying interpolation here is not the best idea. However, we are going to do it for practical purposes. When the time comes that linear interpolation will be only the solution technique, then we need to understand how to use it. So here in this simple practical example, we are going to understand it. Now you see, if we are going to apply a linear interpolation for the f over p value for 8% interest rate for 37 years, we are just going to look at the f over p values under 8% interest rate for 35 and 40 years, because these are the closest available values in the compound interest tables. Now let's check that out. Let's share the compound interest table. And for 8% interest rate, so for 8% interest rate, so let's go back a few pages. For 8% interest rate, we are looking for a single payment compound amount factor. And as you can see, we do not have any row that corresponds to 37 years of investment. So what we have is for 35 years, this factor would be 14.7853. And for 40 years, it will be 21.7345. So we are just going to record these two values at this point. And if we go back to our presentation file, you will see that in this formulation, we are calculating a weighted average of the two closest compound amount factors for f over p, which are for 35 and 40 years, and these values are as recorded from that table. Now we are going to take a weighted average of these two values. Now you see, we are interested in 37 years. And what we have is 35 and 40 years. Now 37 is much more closer to 40, as you can see. Therefore, the weight of the compound amount factor for 40 years should be, 37 is much more closer to 35. Therefore, the weight of the compound amount factor for 35 years must be greater, right? So what we are going to do is, we are going to assume that this linear interpolation is applied between 35 and 40 years. And I'm just going to show that to you in a paint file. So I'm just going to share a paint file with you now. All right. So this is just going to be our page where we apply the linear approximation. So what we are going to do is this. We are going to draw a two-dimensional plane, and here we are going to have the number of investment years n, and here we are going to have the single payment compound amount factor f over p for 8% interest rate for n years, okay, as a function of the number of investment years. And what we know is for 35 years, and for 40 years, we have two values observed in the table, right? So we know that for 35 years and for 40 years, we have two values that have been observed. And what are these two values? So let's write them down. For 35 years, the value for single payment compound amount factor is 14.7853, and for 40 years, it is equal to 21.7245. All right. So what we are going to do is, we are just going to apply a linear interpolation between these two values. And we are interested in, for 37 years, what is the compound amount factor? Okay, we are going to find that value. And what we are going to do is, we are going to multiply this value. We are going to multiply this value with what? With the distance between 35 and 37, which is 2. Okay? And we are going to multiply this value with the distance between 40 and 37, which is 3. And we are going to make this summation, and and we are going to divide this summation to 5, the total of the weights. Okay, so basically this is the thing that we are going to apply. And if we go back to our presentation file, you'll see that that is exactly what we are doing. So the compound amount factor at 35 is multiplied with the distance between 40 and 37, which is 3. And the compound amount factor at 40 is multiplied with the distance between 37 and 35, which is 2. And the summation is divided by the total distance between 40 and 35. And the result, the approximate result, is 17.56 approximately. Now, the thing is, this value can easily be computed through the actual formula, and the actual result, if you do not apply a linear interpolation, but if you are interested in finding the exact result, it would be 17.25 approximately. Now you see, is this an approximation, good approximation? Actually, it is not, but there will be times in our future lectures where the linear interpolation will be the only solution to identify the answer of the problem. Now we are going to apply another linear interpolation. So it says approximate the uniform series compound amount factor for 6.75% interest rate and for 15 years. Now we know that for 15 years of investment, we have available values in the table. However, we do not have any page for 6.75%. And again, we are just going to look at the closest values in the compound interest tables. So let's check them. In the compound interest tables we are interested in the number of investment years of 15, and we are just going to check 6.75 in the table, but it is not available. So for 6% interest rate, the uniform series compound amount factor for 15 years is just 23.2760, and for 7% interest rate, it is just 25.1290. So we have these two values available, and we are just going to record those, and we are going to apply a linear interpolation between these two values. And if we go back to our presentation file now, what we are going to do is we are going to weight the uniform series compound amount factor for 6% interest rate with the smaller of the weights, and at 7% we are going to multiply this factor with the larger of the weights. Why? Because 6.75 is much more closer to 7 than 6. And how do we determine the weights? The weights of these compound amount factors will be determined by the distance of 6.75 to the opposite input. So at 6%, the compound amount factor will be multiplied with the distance between 7 and 6.75. And at 7%, we are going to multiply it with 6 minus 6.75 minus 6. And we are going to divide this to the total distance between 7 and 6%. And the result will be simple to calculate. So the values that we were looking for were 23.27 and 25.12. And the result will be approximately 24.66. And the actual result by the formula is 24.65. Now this time you see we have a better approximation. Here it is not a bad approximation. Sometimes the linear interpolation application works just fine, but remember again for this example, for the second question, using the formulation was the best option. All right, so we have learned the linear interpolation, and we are going to continue our class in the next video.